Hello, my name is Mark Kuzik, and I'm a professor of physics at Washington State University. I spend quite a bit of time doing research, writing papers, and teaching, and all of that is quite time consuming. And a lot of it involves me sitting at my computer and using the keyboard. So I thought this medium of making a video would be a lot easier than having to very carefully edit a document. And so what I plan to do is to talk to you like this without any preparation and to talk sort of from the top of my head. And so you'll see that I will not always have a very coherent way of presenting things, but I'll try to get my thoughts across as best I can. And I would like to talk about a lot of different topics. I'm interested in a lot of different things. I like to think about things that go beyond my field. And these will be the kinds of things I will discuss, but I'll also talk about things within my field that I think are interesting and would be understandable to a general audience. I value intelligence above being smart. And if you look at the dictionary definition of being smart and being intelligent, intelligent is defined as something innate in the individual, where smart is something acquired. Now, to me, the distinction is a little bit different, and this is just based on the usage of the word that I have heard, is that someone, let's say, who is very good at mathematics and can solve any problem, I would say they're smart. They're not necessarily intelligent. The intelligent person would be someone who would be thoughtful and would be able to understand the idea behind some of the mathematics without necessarily having to actually do that mathematics. I guess the simplest example of that would be writing, since I mentioned writing in the beginning. When you write something, you need to use the language, you need to be able to spell words and use grammar. And so I think that, someone who knows how to use grammar perfectly, can spell any word, knows all the nuances of the language, I would call that person smart. But the person who writes a very thoughtful piece that makes you ponder deeper issues, that person is intelligent. So even though they make mistakes in what they've written, in their grammar maybe, or their spelling, they still are talking about something that's interesting and something that you want to hear about. Whereas a smart person might be able to do things mechanically and by rote, but they don't necessarily talk about things that are of interest. So I'm hoping to talk about things that are aimed at intelligent people. You might not have the mathematical background to understand things that I want to talk about, but I'd like to discuss things in a way that would make sense to someone who's intelligent. So that's my take on the audience and on the kinds of things that I would like to talk about. So on that topic, I think that everybody has some balance between intelligence and their level of smartness. And to me, I like someone whose level of intelligence is high, independent of how smart they are, although being ignorant is not a good thing. So you need to have some background in whatever area so that you can intelligently think about a topic. And so one example of this is just in the history of the development of something like the general theory of relativity, which I think is a wonderful example. People generally think of Einstein as being very smart and a very good mathematician. But it turns out that he had a lot of trouble with mathematics. People who have analyzed his notes when he was developing the general theory of relativity find that he went in circles, he made mistakes, he went through the same kind of hardships that a typical student goes through when they're learning general relativity. I haven't seen his notes, I'm just recounting something that I've read, but I think it's interesting that he had difficulty with his mathematical skills. But I think he was very intelligent because he had this very deep thinking process. And so to give you an example, the kinds of things that he thought about are things that anyone could think about, even without any mathematical background. So for example, in classical physics, we have a coordinate system that you use to define the position of some event, or let's say the position of a particle. And typically you have three axes, X, Y, and Z. But even a one-dimensional coordinate axis is something that everyone is familiar with. That's just a ruler. And a ruler will measure, the distance between points. And if you imagine extending that ruler out to infinity in the plus and minus direction, that's the example of an axis. Similarly, time is something that we all know about. We look at a clock and we can see the second hand of a clock moving. Or if you just look at a digital watch, you see the seconds passing, tick, 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 like that. And so we know that it has something to do with the time interval. Before Einstein, people thought that time and space were independent, so that you could measure the position of something, you could measure the time at which an event happened, and that was very well defined. And it didn't matter where the observer was. The observer could be on the other side of the universe, they could be standing on their heads. Wherever they were, they would observe that same phenomenon. But what Einstein was thinking about was the fact that the world is not that absolute. And so he was picturing light beams traveling, and he thought about the proposition that perhaps the thing that's absolute are not the coordinates, but the speed of light. Okay, so that takes a lot of thought process to come up with. It doesn't require any mathematics. He just said that the coordinate systems aren't absolute. It's the speed of light that's absolute. Now, how did he come up with that? Well, as usual, in science, there's a literature, people are doing experiments, and they get data. And sometimes the data is very puzzling. So let me give you a little background on where this general theory of relativity came from. Or, I'm sorry, just special relativity, not even general relativity. And that is that people were studying various kinds of waves. So for example, a sound wave, when I'm speaking to you, my vocal cords are vibrating, and it makes little bursts or puffs of air, and they travel as a wave towards the microphone, and then the microphone vibrates and picks up that sound. And so people were familiar with those kinds of waves. They could make waves, let's say like in rubber bands, when you pluck a rubber band, a wave propagates. And in all cases, waves were associated with some material that was moving. Now, the big puzzle came when people started studying light. They realized that light was a wave. How did they know light was a wave? Well, just looking at light, you just see a beam of light or a ray of light. It doesn't look like a wave. Well, the way they determined that was that when you take two beams of light and you make them propagate together, you get an interference pattern, sort of like water waves. If you have two water waves traveling at each other, when they meet, the amplitude of the wave gets bigger because it's additive. Or when the trough and the peak add up, it cancels out and you get nothing. So similarly, when you mix beams of light, you can get dark and bright spots depending upon them being shifted in their propagation. And so because light acted like a wave, people thought, well, there must be some medium that's required to make light propagate. And so people were trying to measure this medium, and they called it the ether. And one of the measurements they did was using an interferometer. This was done in Cleveland, Ohio. And the apparatus was a Michelson interferometer. And it's basically something that splits a beam of light into two pieces. And it's able to measure this interference between those pieces. And the idea is that the Earth, when it's orbiting the sun, it's moving very, very quickly, or the velocity is very high. I should be careful of the words that I use. And so they figured, well, if we take this Michelson interferometer, if we align one of the arms with the direction that the Earth is moving through the ether compared to that perpendicular direction, we'll see some interference pattern where that motion through the ether is going to change the way the light's propagating. And then if we rotate that interferometer in the other direction, so now this arm is aligned with the direction of motion, then the interference pattern will change. And so the experiment was very simple. They built this interferometer. I'm saying simple, it's very hard to build such an experiment. But what they did was they rotated this interferometer and they expected the signal to vary as they were rotating it. And when they did that, they didn't see any changes. And so it was a big puzzle. Where is this ether that had to be there because of this propagating wave? To make a long story short, there was a lot of work done to determine the equations of how electromagnetic waves propagate. And there was a term in there that came up over and over again where the speed of light was represented in these equations. And it appeared that certain quantities were constant. And it was there that Einstein noticed that it might be possible that the speed of light is the thing that's constant. And so what he then did was he assumed it was constant, and then he worked out the consequences. And then the consequences that came out were really pretty phenomenal. And what he found was that if I have two frames of reference, by a frame of reference, I mean, picture a coordinate system that someone is sitting on. So a coordinate system has three axes. So someone is sitting here, and here's another coordinate system. If those two coordinate systems are traveling with some constant velocity relative to each other, then each observer will see the other person's clock traveling, or not traveling, the other person's clock ticking at a different rate. And similarly, when you observe one frame from the other, you see the length of the rulers being different. So even if the rulers start out being the same, when there's a relative velocity between the two, each person sees the other person's ruler being a different length, okay? So it's a little bit complicated without equations to describe why that happens. But basically what Einstein did was he said, okay, if the speed of light is constant, then I can make a clock by defining, let's say, the second hand of the clock as being the round trip time of a pulse of light between two mirrors. So imagine these two mirrors and the light's bouncing back and forth between, and we define the unit of time as the time it takes the light to travel between these mirrors. And so that way, when one frame of reference was moving relative to the other frame of reference, then you could see that there would be some funny thing happening, because in the classical theory, when there's relative motion between the two frames of reference, the amount of time it'll take the light to go from one mirror to the other will be different than if the coordinate system isn't moving. But if the speed of light is a constant independent of coordinate frame, then things are different. So anyway, the beauty of his theory is the assumption is very simple, and that is that the speed of light is constant in every frame of reference. And you just make that assumption and you define a clock, and then from that clock you define a way to measure distance, and you put it all together and you get the theory, the special theory of relativity, in which case position and time are no longer absolute quantities of an event. And in fact, the very interesting thing that comes out is that as you're traveling at some velocity relative to another frame of reference, what ends up happening is that position turns into time and time can turn into position. So that's very abstract. But in the end, the idea is that instead of having three coordinates, x, y, z, there's a fourth coordinate, time, and we can't see that spatially because x, y, and z are the spatial coordinates. The time coordinate is something that we can't see, but we can measure with the clock. But when you look at physical processes, these processes behave in a way where those three positions in time are on an equal footing. And so we can now think of space as being four-dimensional. So just like if I have a coordinate system where I have an object like this screw that's along the x-axis, if I rotate the coordinate system, I can make it sit along the z-axis. Now, in relativity, I rotate this coordinate axis by moving relative to that object. And when I move relative to that object, the coordinate frame rotates so the position turns into time. It's a very, very weird thing. Now, the final question I may get from many of you, or the confusion that you might have, is that you might say, how can that be? That is so weird. I do not understand that. Well, what I would say is that that's what happens. And the problem is you are using your classical way of looking at things to try to understand the process. And the point is that classical mechanics don't work. You really need relativity. But luckily, these effects require the velocities to be a large percentage of the speed of light. So typically, you won't see these things. But if you travel fast enough, you will see these very weird effects. And so one thing that I find a lot of fun about being a physicist is that we often learn things that are very counterintuitive. But we do experiments, and when the experiments show that these counterintuitive things are happening, we accept them. And so one of the things that we have to learn is to accept things that are very strange. And we accept them because the experiments show that the universe is made in that way. And so physics is kind of liberating because we're not in a jail where we can only think a certain way. We can see how we are required to accept things that come out of our experiments. Now, on the final note here, and you can see I'm rambling on, and I can go on for hours, but I'll try to cut this down to a reasonable amount of time. It's ironic that Einstein, here he came up with this crazy theory that happened to be correct, and he was able to accept it because experiments showed that this was happening. But then when quantum mechanics was first proposed, Einstein didn't want to accept it because he felt that the universe was deterministic, whereas quantum mechanics added a statistical or a probabilistic component to it. And he had that famous quote, "God does not play dice," because he just couldn't believe that quantum mechanics could be true. Ironically, quantum mechanics is true. The very, very strange things happen. And there are some very interesting experiments, which I won't go into details now, but I'll just kind of whet your appetites. You can read about John Bell, where he came up with experiments that you can do to test to see if the laws of physics are deterministic or not. And so look up the term Bell inequality, and you'll see the ideas behind that. So I think this is enough for my general introduction. So in conclusion, I'm hoping that I can describe things in general ways to people that might not have the mathematical sophistication, but that they're intelligent and that they have questions and that they want to understand things. And hopefully we can develop a dialogue online on these topics. So as an experiment, we'll see if maybe we can come up with a dialogue on this YouTube channel. And I'll continue to post these videos. And if I don't get any responses, I'll still continue doing it for a while just to get these things off my chest. And we'll take it from there. So thank you very much for listening, and I'll see you next time.